I'm Anil Kumar, and in this video, we'll derive a general formula to consider the examples based on throwing a stone from a mountain cliff and finding its height at any time or time when it hits the ground. So let us consider that this is kind of a cliff for us, right? So let's say this is the cliff for us. And let us consider that this is just C here. Okay. In that case, what we are doing at this stage is we're just throwing a stone from this place and kind of, let's assume that goes kind of like this, right? So that is the movement of stone, and the idea is to find the height of the stone at any instance of time or time when it hits the sea level, right? So that's the kind of problem which you'll come across, and we'll derive a general formula relating the height, in this case, velocity, acceleration, and time. That's the idea of this particular video, right? So let's begin by defining some variables. Let us say that the height of this mountain, so we call them initial conditions, right? We'll begin with initial conditions and let the height be h0, and let's say time at this time is t0. These are initial conditions at this instance of time. Velocity be v0, right? Now here what you will always observe is that acceleration is always constant. Acceleration is, if you're doing in meters per second, it is 9.8 meters per second square. That is in MKS unit. We normally take this as negative because it's kind of acting downwards, but if you're doing an FPS system, then you could take this as minus 32 feet per second, right? So second square. So that could be in a different system, right? So these become your initial conditions, and important thing here is that the final condition will be, this equation is only valid till the stone is in the air, right? So when it touches the sea level, at this time the movement will be different, so we'll have a different equation. But for this duration, we'll call this time when it hits the ground as t final, right? So this normally we may have to find, and we know one thing, that height final will be 0 because that becomes our reference point, right? So, and we'll also try to find what is the final velocity. So these are the parameters which we need to connect, and in this exercise we'll do exactly that, right? Once we do this derivation, then you can actually use this concept to solve any related problem, correct? So let's begin from the top itself, and let us say that here the stone is dropped, whether it is thrown upwards, downwards, or just dropped. So depending on that, the velocity could be positive, negative, or 0. But in this case, we'll keep it v0, just a general thing. Height h0 is actually height of the mountain, and so what we are saying here is that the height of the cliff, rather, or the place from where it has been dropped, is h0, right? So this is the height we are talking about, height of the cliff. Okay. Now overall, when you're close to the surface of the earth, acceleration is constant. We'll take MKS units and we'll take this as minus 9.8 for the time being. Okay. Now acceleration, as you know, is equal to what? Acceleration, A, is also rate of change of velocity. That is how we define acceleration. So I could write here dv dt equals to minus 9.8. Correct. Now we have differential on the left side, so it becomes a differential equation. You will learn this as first order ordinary differential equation. Now to solve such a differential equation at present, we can do antiderivative. So the process is to take antiderivative those of you who have learned integration can integrate and get the result. So it is a constant. Antiderivative should be a constant times the independent variable, and what we get from here will be velocity equals to minus 9.8 t plus some constant. Let me call this as k. To find this constant, we should use initial conditions, right? So to find this constant, we are going to use initial conditions, which for us is at t equals to 0, velocity is equals to v0. That is the initial condition. We'll substitute those values here. So what we get here is that v0 equals to minus 9.8 and t0 is 0 for us. Okay, I wanted to write t initial as 0. Anyway, let me write 0 here plus k. And clearly, k, this is 0, so k is equals to the initial velocity. That is the initial condition. Perfect. So you could write this expression of velocity as minus 9.8 t plus initial velocity v0. This is a very important equation. Let me just highlight this one. Right, and this is the constant acceleration based on which we have done all this derivation. Let me call the first one acceleration 1 as equation 1 and this one as equation 2. Okay. Now, what is velocity? Velocity is rate of change of displacement. In this case, height is changing. We could call it dh dt, correct? So I'll replace this by dh dt, rate of change of height, and then the equation could be now written as minus 9.8 t plus v0. Again, as you see, this is a differential equation. We'll do antiderivatives. Let me use this symbol here. So we'll do this operation to figure out what should be the h value whose derivative is this. That is what antiderivative is. And from our past experience, we know this should be minus 9.8 t square, half of that divided by 2, right? Plus v0, it is known constant, will get multiplied by t, and plus some other constant. Let me call this as c. Now here again, as we did earlier, we'll apply the initial conditions, and at this stage, at t initial, starting with, it was 0, right? So I should have written this is time is 0, right? Okay. And at this time, the height is h0, which is height of the cliff. So this is actually height of the cliff, right? Height of the cliff. Okay, so once you substitute those values here, you get h0 equals to, this is 4.9. Therefore, you always see minus 4.9 in your equations when you're doing in meters, MKS units, right? V0 times 0 plus c, and clearly c is equals to the initial height, which is height of the cliff. Once you substitute this back into your equation, you get the function of height. So height is now related with time as minus 4.9 t square plus initial velocity times t plus the constant, this time is height of the cliff. So that becomes your equation, which is relating height, time, and velocity. In this scenario, when the movement is vertical and it is because of the external force, which is due to the gravity of the earth, right? So, and that is constant. So we started with the constant gravity of the earth. Did antiderivatives twice to get this third equation. Now these three equations are extremely important equations to solve any question which is based on tossing a coin off the cliff and then finding time or the height at any instance, right? So these are the three equations which we'll be working on important thing is these are also the major steps which you have to follow to solve such a problem. I'm Anil Kumar, and I hope in very simple language it tells you a way of solving such related questions, right? You can always share and subscribe to my videos, and if you like, you can put some likes. Thank you and all the best.